Hello class, and thank you for watching. In topic 2.1, change in arithmetic and geometric sequences, part 1, you're going to learn to express arithmetic sequences found in mathematical and contextual scenarios as functions of whole numbers. Let's begin by first going over what a sequence is. A sequence is a function from the set of whole numbers to the set of real numbers. So a sequence is another example of a function where we have a function that's going to go from our whole numbers. Let me draw the symbol for whole numbers correctly. Okay. And it's going to go to the set of real numbers. Now, because we input only whole numbers, which start at 0, our whole numbers, remember our set of whole numbers start at 0 and it goes 1, 2, 3, 4 and so on. Again, our whole numbers. So only inputting those as our input values, our answer is going to be any real number, any positive, negative, fraction, decimal, whole number, rational, irrational. So as a result, the graph of a sequence consists of discrete data points instead of a curve. So for example, here I have an example of a sequence on the left side. This is what the graph of a sequence will look like. And this is what the graph of a non-sequence of a regular function will look like. Okay? Because the input values that we're only allowed to input for the values of x, or in this case n, are going to be the whole numbers of 0, 1, 2, 3, 4, 5. While here I'm allowed to pick any number between 0 and 1, 1 and 2, 3 and 4, and get actual values and y values as a result. So that's why the points are all connected. Now in this lesson, or in this course, we're going to study two specific sequences: arithmetic sequence or arithmetic sequence and geometric sequences. Today we're going to focus only on arithmetic sequences. Now, an arithmetic or arithmetic sequence behave like linear functions, so they behave like lines, except that they're not going to be continuous. Successive terms have a common difference or you can consider it or think about it as having a constant rate of change. Now the formula for an arithmetic sequence is very similar again to that of a line. So remember, for the ones of a line, y equals mx plus b, right? Well, the equation for an arithmetic sequence looks very similar to this, where we have a slope and a y-intercept. But instead of using y and x, we use a different notation. We use this notation here. We use a sub n equals a sub 0 plus d times n. Where a sub 0, fix this on your notes, that should be a 0 down there, is the initial value. In terms of a function of a y, that's your y-intercept. D is your common difference. Again, correlating back to the line, that's going to be the slope of the line. And a sub k is the kth or the kth term of the sequence. Okay? Which we're going to talk about right now. So in this formula right here, this would be your y-intercept. This right here would be your slope. This would be your x value, and this one right here would be your y value. So y equals to b plus mx. It's just written backwards, but the same thing. Y equals mx plus b, where this is your x, this is your slope, and this initial value is essentially your y-intercept. The other formula that we also have for the arithmetic sequence is that a sub n is equal to a sub k plus d times n minus k. This is one that more than likely are going to use, and we use this one when we do not know what the y-intercept is, and we have, again, instead of 2 points, is not the initial number in the sequence, the first point in the sequence. This is the most commonly used one and the more helpful one. where a sub k, like I said, is the kth term of the sequence. Now, a couple things that you should note about this, that arithmetic sequences again behave exactly like linear functions, again, except that they're not continuous, meaning that increasing arithmetic sequences increase equally for each step. In other words, the slope always stays the same, and the same thing if it was going downwards. Decreasing arithmetic sequences always decrease equally each step, so they go down by the same value every single time. Now, what do we need to know how to do with these? Well, the first thing that we need to know how to do with these, change my settings to seamless, is know how to evaluate a sequence using its formula. So let's consider the sequence defined by a sub n is equal to 4n minus 3. And we want to find a sub 1. To find a sub 1, we're simply replacing the value of n with the value of 1. So just like with function notation, this is no different than thinking about this as the function of f of x is equal to 4x minus 3 and trying to evaluate my function when x is equal to 1. We would just simply use direct substitution and replace the value of x with 1. Well, the same thing is happening here. Let me erase this. The same thing is happening here. To figure out what a sub 1 is equal to, we're simply going to replace the n value with 1. Again, this number right here into the value of n, and then simplify this expression. Well, 4 times 1 is 4, and 4 minus 3 is equal to 1. So a sub 1 has a value of 1, which means that not the initial value, but the second value, because every sequence starts with a sub 0, is going to be 1. So this is the first value in the sequence. Now, to figure out the seventh value of the sequence, a sub 7, we just simply do the exact same thing. Replace again the n value with 7 minus 3, and this will be 28 minus 3, which is 25. So a sub 7 equals to 25. Now, the second thing we're going to do now is, okay, how do we figure out this sequence? How do I determine, again, the value of a sequence if I have, again, two different numbers? So a sub n is an arithmetic sequence with a sub 3 is equal to 7 and a sub 4 is equal to 9. Let's find an expression for a sub n and use the expression to find a sub 24, so the 24th number in the sequence. Well, to figure out this value, we cannot use this function here, because we do not know these two things. We do not know what the initial value is, okay? And we do not know what the common difference is, at least just not yet. But we're going to figure out what the common difference is by doing some arithmetic. Now, again, because these things behave exactly like lines, the way we're going to figure out the common difference is by using essentially just our slope formula. And instead of using that formula, we're going to use this formula instead. A sub n is equal to a sub k plus d times n minus 1. And because d, again, is like the slope of a line, d is just, again, the common difference, and which is essentially just basically like the slope of a line, we're going to use our slope formula. But in this notation, using, again, this notation, this would be a sub k minus some a sub, I'll call it m value, divided by k minus m, where these values are going to be, again, the 2 points that were given, 7 and 3. So I start by getting the larger value of 4, and I subtract it by 3. That's going to be the k and the m down there. And a sub k relates again to the value that it equals to, and a sub m relates to the value of that value right there. So the common difference here is going to be a sub 4 minus a sub 3 divided by 4 minus 3. So if I substitute in a sub 4 with 9 minus a sub 3, the value of that is 7. 4 minus 3 equals 1. And 9 minus 7 equals 2. So this equals to 2. So there. Now that I know what the common difference is, I can now figure out what the formula is. A sub n is going to be a sub k. Since I use, again, you always make the k value the larger value right here. So this one right here is going to be my a sub k. So I'm going to replace this value in of our function with this number right there, 9. We're going to add the common difference, which we now know is 2, and we're going to multiply that by n minus k. That should be a k, I'm sorry, not a 1, k. And our k value is this number right here, 4. And there, that is the equation to our arithmetic sequence. We can simplify it by distributing the number 2 and then combining like terms. Since the like terms here are 9 and negative 8, that's going to simplify to 1. So 1 plus 2n. And this again is our sequence, the formula to the expression to our arithmetic sequence. A sub n is equal to 1 plus 2n. So if I want to figure out a of 24, now that I know what the sequence is, the expression for the sequence, I just now simply have to replace the n with the number 24. Well, 24 times 2, that's a total of 48 plus 1, that's going to be 49. So this is the value of a sub 24, I'm sorry, a sub 24 equals to 49. Now, for this next example, we don't have to figure out the common difference again that as difficult. Well, the way to find the common difference isn't as difficult because we have a graph. Remember, the common difference, it behaves exactly like the slope. So if I can get the difference from the rise over the run, right here, I see that I go down 2 over 1. So the common difference is negative 2 over 1, which just as simply reduces to negative 2. Negative 2 over 1, negative 2 over 1, and again, negative 2 over 1. That is the common difference every single time. So again, these arithmetic sequences behave exactly like lines. And on this example, I don't have to use the general form. I can use this specific one. A sub n is equal to a sub 0 plus d times n, because I know what the initial value is. Here, a sub 0 is going to start this function start at this value here. A sub 0 is equal to 8, the y-intercept. This, remember, is referring to the initial value. And on the graph, that initial value is a y-intercept. And as you can see again in this picture, we crossed the y-axis at 8. So that would mean that the initial value would be 8. So this function is 8 plus negative 2 times n, or 8 minus 2n. And now that I have the expression, I can now evaluate a sub 12 by simply replacing the value of n with 12. Which this equals to negative 16. So there you have it. This is what you need to know how to do with arithmetic sequences. Know how to evaluate an arithmetic sequence. So if you're given an arithmetic sequence, know how to figure out any term in the sequence. How to use 2 points or 2 numbers in a sequence, and only 2 numbers in a sequence, to determine again what the formula or the expression to the sequence is, and then use it to evaluate it. And the same thing with a graph. If we're given again a specific term in the sequence, we can then do that. The good thing about this is that this right here, the graph again, also gives us the list of the numbers in our sequence. The initial value in our sequence is 8. The second number in the sequence is 6. Again, we're looking at the y values here. The third number in the sequence is 4. So on, and the last number right here is going to be 0. So we have 2, 6, 4, 2, 0. I'm sorry, 8, 6, 4, 2, 0. And then again, the sequence keeps on going. But as you can clearly see, when we're given whether it's a graph or an actual list of what the numbers in the sequence are, then we can use this formula here to determine the expression of our sequence. But if they do not tell us what the initial part is, what the starting point is, then we would have to use the general form, this one up here, which is, again, is the most common thing that occurs. That they'll give you, again, 2 points in the sequence. And the way that we figure out the common difference is basically just y2 minus y1 over x2 minus x1, where these numbers, again, are my y2 and y1, and the subtext on the value of a is my x1 and my x2. So that's how I figure out the common difference. And then from right there, I substitute it in, simplify like I did at the previous example, and I get my expression. But anytime I'm giving, again, the first term, I can automatically use this one because I know the first term is going to be the first number there. And then I just look at what the common difference is. From a graph or from this list, it's easy to see, again, that you're decreasing by 2, which can be calculated by simply subtracting any number in the sequence and subtracting it from its previous one. So 6 minus 8 is negative 2, 2 minus 4 is negative 2, 4 minus 6 is negative 2. So if you get any term and divide it by its previous term, that's how you're going to figure out, again, that D, that common difference. All right. Well, this again, this concludes our lesson on arithmetic sequences. Like always, I appreciate you watching. And if you do have any questions, please do not hesitate to email me or send me a message on Parrot Square. And like always, thank you for watching, and I hope you have a great day. Goodbye.